Hello everyone, I'm Chaitanya Roygaga, and today I'll be presenting our paper APE-V, Athlete Performance Evaluation using Video. Athletes of any caliber, from professionals to first-time amateurs, try to limit injury while maximizing their training and exercise. At the professional level, this balance is facilitated by trainers and coaches who perform expert-level assessments of athletes and customize their training plans. Accessibility of the same equipment or trainers is a concern for amateur athletes. A computer vision system that performs personalized assessments using only RGB cameras, which are available in most modern devices, would scale to athletes of all means. As an initial step towards such a system, we annotated a dataset of correct and incorrect evaluative jumps and trained machine learning models to automatically identify when jumps have been performed incorrectly. This is a crucial step as incorrectly performed jump motions are unsuitable for performance evaluation. For our experiments, we used two types of video information, raw frames and pose information from OpenPose. A correct evaluative jump performed by a participant has a few characteristics which we use to identify 14 pivotal errors in jumps. First, the participant assumes a straight posture while looking forward, jumping high enough after an initial squat, and then landing back in a similar position from which they started. During these jump motions, the participant might not start with the correct position, or they might perform an irregular landing. Additionally, for the drop jump, the participant drops from a box onto the force plate. A well-executed drop culminates with both feet touching simultaneously, followed by a quick reflex jump. Associated errors include jumping instead of dropping, or lingering onto the force plate for too long, rather than immediately jumping. Two expert annotators labeled a subset of the data, and Cohen's kappa was used to assess the inter-annotator agreement. We used joint coordinates detected from OpenPose for hips, knees, and ankles to train LSTM models. We also processed the videos to select a subset of keyframes for evaluating another set of models with less dense temporal information. These results show that among the single view models trained on all available frames, the center view provided the best model performance, as it contained more details compared with the left and right view, which may occlude key points. Also, dropping some temporal information when using selected keyframes hurt model performance. For the view fusion model, we combined the individual models trained on the different views for each type of data input. Its performance was better than the single view models for both the full set of confidence frames and the selected subset of keyframes. We evaluated two baseline models, a combination architecture of ResNet 18 and LSTM layers, and the TSM pre-trained action recognition architecture, trained directly on pixel information. We utilized all frames to train these models, as keyframe experiments on pose data led to lower performance. When comparing these fusion models with that trained on the pose data, we see an overall dip in performance. This could be due to extra attributes in terms of image noise being presented to the model, or due to the limited ability of the pre-trained ResNet to extract the relevant features in spite of fine-tuning on the available dataset. Also, the lower TSM model performances could be attributed to the absence of important temporal information, as experiments are conducted with a maximum set of 64 randomly selected frames from the available data. In this work, we presented expert-level error annotations for a jump video dataset to facilitate fitness assessment from RGB video. Further, we provided baselines showcasing that, while these annotations include relatively fine-grained phenomena, it is feasible to identify them with computer vision techniques. Thank you.